Blazé and Douglas from the Open Microscopy environment. And they're presenting the last up.
Right, thank you for surviving this long time to see this talk. I'm very happy that I can present it in front of you, and thank you for organizing the room. We'll be presenting the topic of informatics in bioimaging, or in general how open source software in such a closed domain can be used and how it facilitates new paradigms and user behavior. We are from the Open Microscopy environment. My name is Błażej Kudelski, Bagel Russell. I'm the core developer of the project. Bagel is an external developer from Oxford. I'm from Dundee, Scotland. So thank you for having us, Błażej. So the problem that Open Microscopy tries to solve is basically the data management and analysis in life sciences. Vast amounts of data can be generated by an image acquisition system, which can be a digital microscope, which is in itself very expensive. And that data has to be stored in raw form. Before I carry on, I just wanted to ask one question. Does anyone have any background in biology or computational science in general? Okay, that's fine. So, as an example, the IT infrastructure in Dundee, which runs around 400 terabytes, 13 terabytes of that infrastructure is already taken up by images generated by acquisition systems from Zeiss, Nikon, and other manufacturers. And image is treated as a measurement. I'll explain in a second why is that, and why and how it undergoes quantitative and qualitative analysis. And an example you can see, those are pretty images, quite colorful. In 2 dimensions, they look quite appealing, but what can't be seen here is the spatial information, the temporal information, multi-channel information. So those, in reality, those are multi-dimensional images, and each channel, each modality has to be captured in the raw data. Hence the size of captured data, and hence also the drive towards shareable resources. So open access to those images drives and facilitates the lack of repetitive experiments, which means that scientists can look at a scientific paper, can validate the results by looking at the raw data that's been bundled together with the paper. Systems like that already exist, and they are driven by Open Microscopy. And how that all happens currently, the let's say 20-year-old workflow that happens in biological laboratories. There is a data acquisition system, or image acquisition system to be specific. Images taken by a microscope are treated as raw data and then transferred to the next stage in a closed source format. So each manufacturer of a microscope tries to log in their users into their specific file format, their specific desktop client. So sharing that image between scientists in a single lab or between lab groups can be very, very hard and frustrating, especially if you work in a facility where computational time is being bought by the hour. Then what happens with the closed source format is being reduced in resolution for presentation and rendering in the client, and also the access is local, so not many pieces of software make use of the client-server paradigm that has been in use for now many years. So, seeing the workflow, one might ask how does OME fit in? So, the consortium that we both represent. OME tries to be this broker, this glue that sits in between the image acquisition system, the users, the presentation and storage elements. We don't solve all problems for the scientists, but we try to solve the ones that are the most common. And we also, under the OME umbrella, facilitate cooperation between commercial partners, us developers, open source projects that build on top of our API. So we try to basically facilitate cooperation. What I mentioned about complex images, this is an example of a 281 megapixel image that's being hosted in the JCB Data Bureau. JCB Data Bureau is an online web application that builds on top of the technology that we produce. and allows the users to interact with the images in a very cohesive way. The data in JCP Data Viewer is also open and ready to download, so it's attached to the DOI of the scientific article. So if someone reads an article and wants to see instantly the raw data that was the source of results of that article, that project, that website basically facilitates. There are many other examples like that, like the Stowers data repository. So many academic institutions work on top of our open source project and adjust it to their specific needs. I also mentioned that multiple modalities in images come from the fact that there is also metadata attached to this image. So here's an example of gene phenotyping, which has to go along with the image itself. The image without the specific data being presented this way is just basically half of the value of the whole result. That complexity also means that user interfaces, or the way how an image is imported into the system or used by the user, is becoming complex, so we have to put more effort into designing the user interfaces so that they are intuitive. Speaking of metadata, this is part of our data model that runs on the server and is being used to capture all the metadata that comes from the image acquisition system. Here is an example of an instrument that has a specific objective used with it, a specific setting of aperture, light source, a filter. That all is visible in the clients that access those images. So if someone wants to see instantly what type of apparatus has been used to capture this specific image, it's all available for the user. This is also then exported into XML, so OMTIF and OMXML are two parts of the whole project which allow easy exchange of that image. So if someone exports, let's say, a Nikon proprietary file format into OMTIF, they can give this image to any scientist that wants to see it, and if that scientist works either on Omero, which is the product that we provide to users, or any OME-aware piece of software, they can instantly import that image and not lose any data on the way, and work with it without any being fenced into this specific format. Looking at the implementation details, there is the server itself, which is based on a technology for the middle layer called ICE, produced by Zero C. That's the same product used by Skype to facilitate PubSub type technology where multiple clients speak to a single server or multiple servers. There are two clients that allow the user to work with their images, visualize them, annotate them, and work with them. One is web-based, the other one is desktop-based. Additionally, the data store is based on PostgreSQL. We use also Hibernate, Lucene for full-text search. And we, I think, achieved a certain cohesion of the tools that we use in the project to give the best results to the users. I mentioned clients, so this is Omero Insight, the desktop client written in Java, runs on Linux, Windows, and Unix operating systems. It's extensible. If you Google for Omero Insight agent, there is a very nice documentation how you can write your own plugins for it. There's a public API that allows whoever wants to really do anything with it to extend it in their own way. It also, as I mentioned, metadata is visible on the right. There is a full image viewer with regions of interest, rendering of multiple Z slices through a biological sample, handling of big images. So the zebrafish was an extreme example, but usually images in life sciences can go up to very, very big resolutions. The web client is trying to give the user the similar look and feel and type of workflow. So also the main image viewer, a data browser where one can see data sets and projects. We also facilitate a permission system. So if you imagine a laboratory being divided into research groups, one can easily model that in our system and assign specific users to specific groups and model the permissions between each other's data. This is based on Django, so Python web framework. On the client side, there is JavaScript run to give users this kind of one-page application feeling. And it's also extensible. So again, the API generated from the source by slice. This is a ICE component. Is Python-based, so if someone wants to extend the Python code, by all means. Also, the JavaScript is available and annotated, so people can see the openness of the project. They can trust the algorithms that we use for image rendering and analysis. And as users told us at our users meetings, they like it more than working with a size or week on a piece of software where they don't really know what's happening inside. Can they trust that the raw data that goes through it will remain as the same measurement as before? And on that note, extensibility, I want to hand over to Douglas who will explain more about the concepts.
So I'm going to talk a little bit about extensibility and then how we sort of relate to the open source world. So everything in red here is a place where we can be extended, and everything in blue is the core system itself. So as Balaji said, you can extend the Java client, you can also extend the web client, you can extend the server itself by adding new services to it. And also we have like a scripting engine, so you can write image analysis algorithms, and then they can actually be run through some grid infrastructure. And a lot of that we get from 0C, so we for free by building on top of that. It's also nice because clients you can write them in any language and on any platform. We get a lot of that for free. So as Balaji said, the microscopy world is really proprietary. All the instruments being built, they cost like hundreds of thousands of pounds in some cases. So they've obviously invested a lot of money in it and would like to lock you in as much as possible. So what generally happens is they've written some specific acquisition software which comes with their instrument. So, and then it outputs a specific format. So you're already locked into Delta Vision or some Zeiss format for whatever microscope it is that you've got. Just in my group in Oxford, we have about 12 different types of microscope, and we've got 8 different image formats that come out of those. And each of those can only be really analysed in the tools that the hardware vendor provided. But with only XML, we can start to build generic tools which can then be used by anyone on any image format. So, is anyone from academia at all? A few people. So, I think it's not always a natural fit for academic software to become open source. And I think there are a lot of reasons for this. Like, one is just that people are afraid of having some sort of maintenance burden, like they're obligated to provide service, and or they're just worried about losing their IP. I think maybe the most compelling reason is that a lot of this software in academia is put together quite quickly, so the quality of code hasn't adhered to like strict software engineering principles or anything like that. So there's sort of a reluctance to put it out there because people might laugh at you or whatever. But you know what I mean? We decided to go down this route. So we leverage existing open source software, and it's really crucial because we have this. We're trying to make everyone adopt what we're offering, and if we don't make it open, then I guess people might not choose it. But maybe the most compelling reason that we're open source is that one of the founders of the project actually had to solve living in his basement when he started the project. So as academics, we rely on academic funding to continue our work, and as time goes on, I think the funding agencies are realizing that it's more expensive to do an open source project. Well, to do a project of sufficient quality that you're willing to put it out there and try and keep it going for a long time. And I think it's slowly being realized that putting more money in makes it more sustainable in the long term, instead of it just being mothballed, which I think happens to a lot of academic projects. The project comes to an end, the person who wrote the code disappears to another job, and the code just disappears into nowhere. So obviously we'd like to keep our jobs by continuing funding, but we're also trying to reduce our reliance on academic funding by making it easier for community contribution and for people to apply for their own funds to contribute to Omera from wherever it is that they're from. So we have this kind of consortium model. I'm from the University of Oxford, Elijah's from Dundee, and this is just the people who are sort of invested in the project at a funding level, but there's also loads of other people who are invested in the project on a community level. And we try and actively solicit developers who are working in a microscopy or biological environment, because they have such a unique perspective on what's really required, and they can build individual tools which then are actually useful to users. That's what I am, so I'm at the University of Oxford building tools which are specific to our users. So there are tons and tons of tools in image analysis and for various tasks to do with images and other microscopy measurements. And up until this point, a lot of them would only work with some image formats. But as time goes on, and we can import more image formats into our OMI XML, if the projects then pick up OMI XML as one of their supported formats, then you get a big win there for free. So you start to be able to use the best tool for the job rather than whatever tool you have to, dictated to by whatever image format you happen to have. So Omera has the OMI project has a commercial arm, Glencoe software, and a dual license for all the software. It's really crucial because, as I said, like the hardware lock-in means that without having this facility, the commercial vendor's not so willing to work with you, so you have to be able to release it in some sort of commercial sense as well. But encouragingly, some of the vendors are beginning to use OMI XML as a primary acquisition format, that's really great. And all the time we're seeing pressure from all the users of Omera software on the commercial microscope vendors and image analysis software providers to support us more, either in terms of just supporting the model, or also in terms of pushing data into Omera and getting it back out. So we're funded by the Wellcome Trust and the BBSRC. So we have some obligations to our funding bodies, obviously, but generally our project direction is determined by the community. So we're trying to build something that works for people. So that's what we want to try and do. If you want to find out a bit more about OMI, this is a good place to start. So this is our organisation on GitHub, and or you can also find the OMI website, which has a huge amount of information on it. So this is just some people that are on the project and stuff, obligated with links to images from the work across. And any questions? Any questions?
So I was really glad to hear again the standard refrain of the problem with the quality of software that comes out of PhD projects, the abandonment of scientific code. I'm a fellow of something called the Software Sustainability Institute, which is a UK thing that's set up to try to address this kind of thing. I was wondering what your feelings are in terms of one of the questions that we're addressing in our campaigns. There is for those of us who are research software engineers. We're working in universities to create research code. There's often some tension around creating software, there's writing papers and that kind of thing, which is why one of the campaigns we're doing is to try to say we are research software engineers rather than general RAs or whatever, and give ourselves a label. How does it work for you in your project?
I think in the OMI project, definitely the focus is on writing the software and getting it out. It's always I think it's just fundamentally organised that way. Certainly the project that I used to work on, there was always the pressure to publish as well, and we wrote half as much code because we spent so much time doing that. But I think OMI's just set up that way. It's all about writing the software. The papers are necessary but secondary. There's also quite a big team, so
yeah,
some people can do some.
And exactly the work that other parts of our whole consortium do sometimes translates nicely into a paper in a specific domain. So If you Google metadata matters, there's a paper published on metadata that's being used to any XML and the data model. And I guess we are lucky enough to be able to basically publish that when time arises. So
I think when you've got the scale, you can do that. You can have the division of labour within the team.
I would agree with that.
We're funded mainly by strategic award grant from the Working Trust. So it's designed to provide a platform. I mean, rather than publish in a specific area. Okay.
Yeah.
Can the project import all the different proprietary formats, or do I have to rely on the microscope vendor in order to provide access on
basically what happens is that there's a certain level of cooperation between the vendors and bioformats, which is actually the library which we use to do all these imports. So how much they collaborate determines how easy it is for us to write the import software. But there's a lot of reverse engineering going on when they're not cooperative.
We don't get we don't get the specification. We just sit down and start reversing.
Well, I said to always just send us the data.
Yeah, if someone comes to our list or discussion groups and says, I'm working with this manufacturer of the microscope, can't use my image in Merrill. We just say, can you just have one sample image, send us the data, we can then work and implement a reader for this specific format and bioformats. Which also means that bioformats is used, and that's the community aspect. Many projects use bioformats like ImageJ, Fiji, they rely on bioformats as a kind of general purpose library, which you can do as well, due to the packaging and distribution system around it. You basically can take bioformats and use it in other places as well. So bioformats, that's probably that's the answer to your question.
I think currently they support 127 image formats.
In your experience, you are some vendors which implement DRM algorithms for their images formats.
I don't really know anything about DRM, and I think, as far as I know, there's no DRM in microscopy. That would be an extra level of meanness.
It's already even a matter of time.
I think the vendors are generally supportive. I don't think they are intentionally trying to. Exactly so. And I think that DRM is generally to prevent the sharing of data. I mean, I think they want to. If you acquire data on their instrument, they want to share it far and wide. Yes. And the microscopes are definitely patent to the heads.
The one thing I wanted to add by answering your format question as well, most of the formats we work with, the proprietary file formats, are TIFF-based. So once we get around the kind of byte header, not going into too much detail, but once we decode the first bytes, it then always falls back to an image file directory, and it's easy to go from there. But yeah, so TIFF seems to be a predominant storage format for proprietary.
So your reverse engineering effort is the right one.
It really depends on the format. I mean, neither of us actually do that bit of the work, but I think sometimes it's not fun. But
especially JPEG formats.
Yeah, I think it's very time consuming. Yeah. Anyone else? Oh.
How do you store these images?
Well, they're stored on a file system. The metadata goes into a database.
You look at object stores?
Given
you've got metadata already and a workplace.
No, definitely it's something to look at in the future. The project's been going for quite a long time, so there's a lot of sort of legacy stuff going on. But I think definitely in the future that's something we should look at.
No, I mean, I guess add about the test that the next iteration of the whole mainline we're working on is called the Merrill FS, and it'll give you the possibility of basically importing the image, and on the file system you'll see the original file as you got it from the acquisition system. So we are going away from a kind of a binary store, more giving the user again the control of all these files. If you don't want to basically be logged into or you can still get the original CCI file or TV file back from the repository on the file system. So that's the next iteration of changes that we're introducing.
One more? Yeah.
Do you have some example of script or of people making, for example, machine learning on your...
So I'm actually working on it right now. We're going to repeat through these probably about months time.
So silence
Basically learning
and we have a repository for user provided scripts. So if someone wants to, say, oh, I came up with this really nice way of phenotyping DNA or working with image, then just come to us or open a pull request on GitHub. We can then review the code and it will be available to the whole community.
Especially if it's high quality decomposition algorithm.
All right, thank you very much.